Tonight, we're going to confront one of the strangest problems in all of physics, the electron. You've seen the diagrams, a tiny ball orbiting the nucleus like a miniature planet. But here's what nobody tells you. When physicists actually tried to measure the size of an electron, they found something that should be impossible. It appears to have no size at all. Zero. Not small, not incredibly tiny. Literally zero, as far as any experiment has ever been able to detect. And yet, this supposedly sizeless thing has mass. It has a charge. It holds every atom together. It is responsible for virtually everything you see and touch. So how can something with no measurable size be the most important building block of the physical world? That's what we're going to explore tonight. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already think you know. The electron. You've seen it 1,000 times. In textbooks, in science documentaries, in animations online. There's a nucleus in the center, a tight cluster of protons and neutrons, and then orbiting around it like tiny planets around the sun, there are these little round balls. Those little round balls are supposed to be electrons. The image is so familiar that it barely registers as a model anymore. It just seems like reality. You picture the atom and you see electrons whipping around a nucleus in neat circular orbits. Maybe some of those orbits are close to the nucleus, maybe some are farther away, but the basic picture is always the same. Little balls, little round spheres, moving very fast, orbiting a center. This picture is called the Bohr model, named after the Danish physicist Niels Bohr, who proposed it in 1913. Bohr suggested that electrons orbit the nucleus at fixed distances, specific energy, levels, and that they could jump between those levels by absorbing or emitting light. It was a revolutionary idea at the time, and it solved real problems in physics. It explained why atoms emit light at only certain wavelengths. It predicted the spectrum of hydrogen with remarkable accuracy. It was a breakthrough, but here's the thing. Even Bohr himself knew the model wasn't literally true. The orbits were a simplification. The little balls were a convenience. The real behavior of electrons turned out to be far stranger than any orbit could capture. And yet, more than a century later, the Bohr model is still the image most people carry in their heads when they think about atoms. A tiny solar system with tiny electron planets. It's intuitive, it's visual, it makes sense, and it's wrong in almost every important way when it comes to the question we're asking tonight. What is the actual size of an electron? To understand why this question is so difficult, we need to go back to the beginning. Back to when humans first discovered that the electron even existed. Because the story of how the electron was found tells you a lot about why people assumed it was a tiny ball in the first place. In 1897, a British physicist named Joseph John Thomson was working at the Cavendish Laboratory in Cambridge, England. He was experimenting with something called cathode rays. These were mysterious beams that appeared inside glass tubes when you applied a high voltage across them. The tubes had most of their air pumped out, creating a near vacuum inside. When the voltage was applied, a glowing beam would appear, traveling from the negative electrode, called the cathode, to the positive electrode, called the anode. The beam would cause the glass at the far end of the tube to glow with a faint greenish fluorescence. These beams had been known for decades. Scientists had observed them and debated what they were. Some thought they were waves, like light. Others thought they were streams of particles. Thomson designed a series of clever experiments to settle the question. He placed electric plates inside the tube, one positive and one negative, and watched what happened to the beam. If cathode rays were waves, like light, they shouldn't be deflected by electric fields. But Thomson saw the beam bend toward the positive plate, meaning the rays carried negative charge. He then used magnets to deflect the beam in the perpendicular direction. By carefully balancing the electric and magnetic forces, he could make the beam travel in a straight line, and this allowed him to calculate the speed of the particles. From the amount of deflection and the known strengths of the fields, he could determine the ratio of the particle's charge to its mass. Only charged particles would respond to both electric and magnetic forces in this way. So Thomson concluded that cathode rays were made of tiny particles carrying negative electric charge. And what he found next was shocking. The charge-to-mass ratio was enormous, about 1,800 times larger than that of a hydrogen ion, the lightest charged particle known at the time. This meant one of two things. Either the new particle carried an extraordinarily large charge, or it had an extraordinarily small mass. Thomson concluded it was the latter. He had found a particle far lighter than any atom, a particle that seemed to be a fundamental building block of matter itself. He called it a corpuscle, though the name electron, which had been suggested earlier by the Irish physicist George Johnstone Stoney, eventually stuck. Now, here's what matters for our story. Thomson's experiments told him the charge and the mass of the electron, at least their ratio. But they told him absolutely nothing about the electron's size. Nothing. He knew the electron had negative charge. He knew it was very light. He knew it could be deflected by fields. But whether the electron was a tiny sphere or some other kind of object, his experiments couldn't say. And yet, almost immediately people began picturing the electron as a little ball. A tiny round object with a definite surface and a definite radius. This wasn't because anyone had measured the electron's size. It was because that's how humans think about things. If something has mass and charge and moves through space, our brains automatically picture it as a small object. A pellet, a grain, a sphere. It just seems natural. In our everyday experience, everything that has mass and takes up space is an object with a surface. A baseball, a grain of sand, a dust particle. So when Thomson announced the discovery of this tiny charged particle, the natural assumption was that it must be a very, very small version of the same kind of thing. A little ball. Thomson himself proposed a model of the atom that reflected this assumption. He imagined the atom as a sphere of positive charge with electrons embedded in it like raisins in a pudding. This became known as the plum pudding model. In this picture, the electrons were definitely tiny objects sitting inside a larger blob of positive charge. Later, when Ernest Rutherford discovered the nucleus in 1911 by firing alpha particles at gold foil and observing that some bounced straight back, the picture changed. The positive charge wasn't spread out in a blob. It was concentrated in a tiny, dense nucleus at the center. The electrons had to be somewhere outside this nucleus, and the most intuitive picture was that they orbited it like planets orbit the sun. But through all these changes in the model of the atom, one assumption persisted. The electron was always pictured as a tiny ball, a little sphere with some definite size, sitting at some location, moving through space like any other small object. Nobody questioned this because it seemed so obvious. What else could it be? But physicists weren't content to just assume the electron was a ball. They wanted to calculate its size. If the electron is a tiny sphere of electric charge, then you should be able to figure out how big that sphere is using the laws of electromagnetism. The reasoning goes like this. The electron has electric charge. Electric charge creates an electric field, and an electric field contains energy. The energy stored in the electric field of a charged sphere depends on the size of the sphere. A smaller sphere concentrates the charge into a smaller volume, which creates a stronger electric field near its surface, which means more energy. A larger sphere spreads the charge out, weakening the field and reducing the energy. Now, Einstein showed in 1905 that energy and mass are related by his famous equation. Energy equals mass times the speed of light squared. If the electron's mass comes entirely from the energy stored in its electric field, then you can set the field energy equal to the electron's known mass energy and solve for the radius. When you do this calculation, you get a number. It's called the classical electron radius, and it comes out to about 2.8 times 10 to the negative 15 meters. That's about 2.8 femtometers. To give you a sense of how small that is, a femtometer is 1 quadrillionth of a meter, 1 millionth of 1 billionth of a meter. The classical electron radius is roughly the same size as the atomic nucleus. It's incredibly tiny, about 100,000 times smaller than an atom. Now, at first glance, this seems like a perfectly reasonable answer. You've used well-established physics, electromagnetism, and special relativity to calculate the radius of the electron. You got a definite number. Problem solved. The electron is about 2.8 femtometers across. Tiny, but finite. A little ball with a definite surface. But here's the problem. This calculation doesn't actually work. It's not that the math is wrong. The math is fine. The problem is with the assumptions behind it. The classical electron radius assumes that the electron's mass comes entirely from the energy in its electric field. But there's no reason to believe this is true. The electron's mass might come from somewhere else entirely, or from a combination of sources. The calculation also assumes the electron is a rigid sphere of charge, a classical object with a definite surface, and this assumption leads to serious contradictions. Here's one of those contradictions. If the electron is a tiny sphere, then different parts of the electron carry different portions of its charge. Those portions all have the same sign. They're all negative, and like charges repel each other. So the different parts of the electron should be pushing each other apart. The electron should explode. What holds it together? In a classical picture, you'd need some additional force, some kind of internal pressure or binding energy that keeps the electron from flying apart under its own electric repulsion. This hypothetical force was actually given a name: Poincaré stress, after the French mathematician Henri Poincaré, who pointed out the problem in 1906, but no one has ever detected any such force. There's no evidence that the electron has internal structure that could generate this stress. No experiment has ever found any hint of an internal mechanism inside the electron that could counteract the electric repulsion. The whole idea of the electron being a tiny charged sphere creates a problem that has no satisfying classical solution. You either need to invent a force that nobody has ever seen, or you need to accept that the classical picture of the electron as a little ball is fundamentally flawed. There's another problem, even more fundamental. If the electron is a point, If it has zero size, then the electric field at its location becomes infinite. The energy stored in that field becomes infinite. And since energy and mass are equivalent, the electron should have infinite mass. Obviously, it doesn't. The electron has a very specific, very well-measured mass, about 9.1 times 10 to the negative 31 kilograms. This is the problem of the self-energy of the electron, and it plagued physics for decades. If the electron is a point, the math blows up to infinity. If the electron is a tiny ball, you avoid the infinity, but you introduce other problems like the need for Poincare stresses and the arbitrary assumption that the electron's mass comes from its field energy. Neither option is satisfying. Neither option works cleanly. The electron was resisting any attempt to be described as a simple classical object with a definite size. This was one of the great puzzles of early 20th century physics. And it was a hint, a very strong hint, that something fundamental was wrong with the way people were thinking about the electron. The problem wasn't just technical. It wasn't just that the calculations were hard or that the experiments weren't precise enough. The problem was conceptual. The entire framework of classical physics, the framework that treats objects as little balls with definite positions and definite sizes, was breaking down at the scale of the electron. The electron was telling physicists that their basic assumptions about what a physical object is and what it means to have a size needed to be rethought from the ground up. Let me pause here and make sure you understand why this is so strange. Because in everyday life, size is one of the most basic properties anything can have. You don't question whether a baseball has a size. You don't wonder whether a grain of sand has a diameter. These things obviously have physical dimensions. You can measure them with a ruler, you can compare them. Bigger, smaller, round, flat. Size is fundamental to how we understand the physical world. Everything we encounter in daily life has a size. Your body has a size. A cell in your body has a size. The molecules that make up that cell have a size. The atoms that make up those molecules have a size, and inside those atoms, the nucleus has a size. At every step, as we zoom in from the human scale to the molecular scale to the atomic scale, things get smaller, but they still have sizes. They're still objects with spatial extent. They still occupy a definite amount of space. So when you get to the electron, you naturally expect the pattern to continue. The electron should just be smaller, a tinier ball, a more minuscule sphere. That's how it works at every other level of reality. Bigger things are made of smaller things, and smaller things still have sizes. They're just harder to see. The electron should be the next step in that progression. A very, very tiny object with a very, very tiny radius. Small, but still there. Still a thing with a size. But the electron breaks this pattern. It doesn't behave like a smaller version of a baseball or a grain of sand. It doesn't have a detectable surface. When you try to calculate its size, using classical physics, you get contradictions. When you try to treat it as a point, you get infinities. The electron sits at a boundary where our intuitive notion of what it means to be a physical object starts to fail. And this failure isn't a small technical detail. It's one of the most important clues about the deep structure of reality. Think about what it means for something to have a size. For a baseball, size is straightforward. The baseball is made of smaller parts: leather, thread, cork, rubber. These parts are arranged in a specific way, and the outermost boundary of that arrangement defines the surface of the ball. The diameter of the baseball is just the distance across that boundary. Simple. For an atom, size is a little more subtle, An atom doesn't have a hard surface. The electron cloud around the nucleus is fuzzy. There's no sharp boundary where the atom ends and empty space begins. Instead, there's a probability distribution that describes where you're likely to find electrons. The atom size is defined by how far this distribution extends, and it depends on how you measure it and what threshold you use. But even with this fuzziness, atoms have a well-defined characteristic size. A hydrogen atom is about 1 angstrom across, which is about 1/10,000,000th of a meter. Different atoms have different sizes, and those sizes are consistent and measurable. The point is that for atoms, size is meaningful even though the boundary is fuzzy. For the atomic nucleus, size is meaningful too, but in a different way. The nucleus is made of protons and neutrons, and these are packed together in a roughly spherical arrangement. The nucleus has a definite spatial extent, about 1 to 10 femtometers across, depending on the element. You can probe the nucleus by firing particles at it and seeing how they scatter, and the scattering pattern tells you how big the nucleus is. The nucleus has internal structure. It has parts. Those parts are arranged in space, and the arrangement has a size. Protons and neutrons themselves have size too. A proton is about 0.84 femtometers across. We know this because experiments have probed the proton's interior and found that it's made of smaller particles called quarks, held together by gluons. The proton has internal structure, it has parts distributed in space, and that distribution has a measurable extent. But the electron is different. At every scale we've probed, the electron shows no internal structure, no parts, no constituents, no arrangement of smaller things distributed across some region of space. As far as the experiment can tell, the electron is not made of anything smaller. It's not a composite object, it's fundamental. And this is the crux of the problem. Size, in the way we normally understand it, is a property that arises from having parts arranged in space. A baseball has a size because it's made of materials arranged in a sphere. A nucleus has a size because it's made of protons and neutrons packed together. A proton has a size because it's made of quarks bound in a particular configuration. But the electron, as far as we know, is not made of anything. It has no parts. It has no internal arrangement. There is nothing distributed across some region of space to give it extent. And without parts, without structure, the concept of size, at least the classical concept of size, doesn't obviously apply. This is not a statement about our ignorance. It's not that we haven't looked hard enough or that our experiments aren't precise enough to see the electron's internal structure. It's that we have looked extremely hard with some of the most powerful instruments ever built, and we found nothing. Every experiment that has tried to probe the electron structure has returned the same result. Point, no size, no substructure, just a dimensionless point carrying charge and mass and spin. The electron appears to be a fundamental entity, not made of smaller things, not composed of parts, just itself. And that fact has enormous consequences for what it means to talk about its size. Let me be clear about something. Saying the electron appears to be a point is not the same as saying the electron is nothing. The electron is very much something. It has a definite mass, about 9.1 times 10 to the negative 31 kilograms. It has a definite electric charge, about negative 1.6 times 10 to the negative 19 coulombs. It has a property called spin, which makes it behave like a tiny magnet. It interacts with other particles through electromagnetism and through the weak nuclear force. It is one of the most well-characterized objects in all of physics. Its properties have been measured to extraordinary precision. The magnetic moment of the electron, for instance, has been measured and predicted with a precision that would be impossible if the electron were not extremely well understood. The agreement between theory and measurement is extraordinary. The electron is real, it is physical, it has measurable, well-defined properties. It's just that one property you would expect it to have, a physical spatial extent, a size in the classical sense, appears to be missing. And this is where our journey tonight really begins. Because of this situation, a physically real object with measurable effects, but no detectable size, is genuinely paradoxical. It challenges our deepest assumptions about what it means for something to exist in space. In our everyday experience, existing means occupying space. Being somewhere means being spread out over some region, however small. Having physical effects means having physical substance, and substance means extent. But the electron seems to violate all of these intuitions. It exists. It is somewhere. It has physical effects. But it doesn't appear to occupy any volume of space at all. How is that possible? How can something be real and powerful and fundamental and everywhere in every atom of your body and yet have no measurable size? This is the paradox at the heart of the electron scale, and answering it requires us to abandon almost everything we think we know about what objects are and how they occupy space. The classical picture of the electron, the little ball orbiting the nucleus, was never based on evidence. It was based on analogy. People looked at the solar system and saw planets orbiting the sun, and they assumed atoms work the same way. They looked at everyday objects and saw things with sizes and surfaces, and they assumed the electron must have a size and surface too. These analogies felt natural. They felt right. But nature doesn't care about what feels right. Nature is what it is, whether our intuitions approve or not. The first physicists to discover and study the electron did brilliant work. But they were products of their time, trained in a classical worldview where objects were objects, particles were tiny balls, and everything that existed had a definite location and a definite size. That worldview was about to be shattered. In the 1920s and 1930s, quantum mechanics arrived, and nothing was ever the same. The electron was the first crack in the classical picture of reality. The tiny ball that everyone imagined was never really there. What was actually there was something far more subtle, far more strange, and far more wonderful than any classical picture could capture. Understanding what that something is requires us to go deeper into the experiments that probed the electron at scales smaller than anything humans had ever explored before, into the theoretical frameworks that replaced the classical picture with something that actually works, and into the heart of a question that still challenges physicists today. How do you describe the scale of something that might not have a scale at all? The journey from Thomson's cathode rays to the modern quantum electron is one of the most dramatic intellectual transformations in human history. It forced us to abandon intuitions that had served us perfectly well for millions of years of evolution. And it revealed that the most basic building blocks of matter are nothing like the objects we encounter in daily life. The electron was where this revolution started. It was the particle that refused to be a particle in the classical sense, the object that refused to have a size. Every other object humans had ever studied could be described in classical terms: planets, cannonballs, grains of sand, molecules, even atoms to some degree. But the electron couldn't. It resisted every attempt to force it into a classical mold, and in doing so, it opened the door to an entirely new understanding of the physical world. That story, the story of how we discovered what the electron really is through experiments that pushed our instruments to their absolute limits, is where we're going next. So we've seen that the classical picture of the electron as a tiny ball leads to contradictions. The math breaks down, the physics doesn't work. But here's the thing about physics. When your theory fails, you don't just sit around feeling confused. You build better experiments. You probe deeper. You find ways to actually look at the thing you're trying to understand, rather than just guessing about it from a distance. And that's exactly what physicists did with the electron. They figured out how to measure the size of things that are far too small to see with any microscope, far too small to touch or photograph or examine in any ordinary way. They developed techniques that can probe the structure of matter at scales billions of times smaller than anything visible to the human eye. And when they turned those techniques on the electron, what they found was one of the most surprising results in the history of science. To understand how physicists measure the size of something as small as a subatomic particle, you need to understand a technique called scattering. Scattering is, in principle, remarkably simple. You throw something at the thing you want to study, and you watch what happens. That's it. You fire a beam of particles at your target, and you carefully measure how those particles bounce off, deflect, or pass through. The pattern of deflection, how many particles scatter at which angles, tells you about the size, shape, and internal structure of whatever you hit. This is actually how you measure the size of almost anything in physics when it's too small to see directly. Think about it this way. Imagine you're standing in a completely dark room, and somewhere in that room, there's an object. You can't see it. You can't touch it. But you have a bag of tennis balls. If you throw tennis balls into the darkness and listen to how they bounce back, you can learn about the object. If lots bounce back, the object is probably large. If very few bounce back, it's probably small. If the tennis balls bounce back from many different directions, the object has a complicated shape. By throwing enough tennis balls and carefully recording every bounce, you can build up a detailed picture of the object even though you've never seen it directly. This is essentially what scattering experiments do. Except instead of tennis balls, physicists use beams of electrons, protons, photons, or other particles. And instead of a dark room, they're probing the interior of atoms, nuclei, and individual subatomic particles. The technique is extraordinarily powerful. Almost everything we know about the internal structure of matter comes from scattering experiments of one kind or another. And the history of these experiments is a history of discoveries that repeatedly overturned what people thought they knew about the building blocks of reality. The most famous scattering experiment in history was performed by Ernest Rutherford and his colleagues Hans Geiger and Ernest Marsden between 1908 and 1913. They fired alpha particles, which are helium nuclei consisting of 2 protons and 2 neutrons, at a thin sheet of gold foil. Most of the alpha particles passed straight through the foil as if nothing were there. This was expected. At the time, the leading model of the atom was Thomson's plum pudding model, which pictured the atom as a diffuse blob of positive charge with electrons scattered through it. A diffuse blob wouldn't deflect fast-moving alpha particles very much. They pass right through. But some of the alpha particles didn't pass straight through. Some were deflected at large angles, and a very small fraction, bounced almost straight back toward the source. Rutherford famously said it was as if you fired a 15-inch artillery shell at a sheet of tissue paper and it bounced back and hit you. This result was completely inexplicable under the plum pudding model. A diffuse blob of charge simply couldn't cause that kind of dramatic deflection. Rutherford realized that the only way to explain the data was if the positive charge in the atom wasn't spread out at all. It had to be concentrated in a tiny, extremely dense region at the center of the atom. He had discovered the atomic nucleus, and he discovered it purely through scattering. He never saw the nucleus, no one could see it, but the behavior of the scattered alpha particles made its existence undeniable. The scattering pattern, specifically the number of particles deflected at each angle, told him not just that the nucleus existed, but roughly how big it was. The nucleus turned out to be about 10,000 to 100,000 times smaller than the atom itself. A tiny dense core surrounded by vast emptiness where the electrons somehow existed. This is the key point. The scattering pattern contained information about the target size and structure. By analyzing that pattern mathematically, physicists could extract that information. This technique, using scattering to probe structure, became the foundation of particle physics. And it was applied again and again over the following decades, each time revealing deeper layers of structure inside matter. In the 1950s and 1960s, physicists at Stanford University performed a series of groundbreaking scattering experiments led by Robert Hofstadter. Instead of firing alpha particles at gold foil, they fired high-energy electrons at atomic nuclei. The advantage of using electrons is that electrons interact with matter through the electromagnetic force, which is extremely well understood. This means you can calculate precisely what the scattering pattern should look like for a target of any given size and charge distribution. By comparing the predicted pattern with the observed pattern, you can determine the size and internal structure of the target with extraordinary precision. Hofstadter's experiments revealed that the proton and neutron are not point particles. They have measurable sizes. The proton has a charge radius of about 0.84 femtometers. The neutron, despite being electrically neutral overall, has a complex internal charge distribution that also gives it a measurable size. The scattering patterns that Hofstadter's team observed were clearly different from what you'd expect if protons were point-like. At larger scattering angles, corresponding to closer approaches and finer spatial resolution, the number of scattered electrons fell off compared to the point-like prediction. The proton was extended. It occupied space. It had a physical radius that could be measured. This was a crucial discovery because it meant that protons and neutrons are not fundamental. They have internal structure. Something is going on inside them. That something, as physicists later discovered, is quarks and gluons. Protons and neutrons are composite objects made of three quarks bound together by the strong nuclear force mediated by particles called gluons. Hofstadter's experiments didn't discover quarks directly, but they showed that protons and neutrons have spatial extent, which implied they must have internal parts. He was awarded the Nobel Prize in Physics in 1961 for this work. Now here's where things get directly relevant to our story. The same scattering technique that revealed the size of the proton has been applied to the electron, and the results are completely different. When you scatter particles off a proton, the scattering pattern deviates from what you'd expect for a point-like target. The deviations tell you the proton has a finite size, You can measure exactly how big it is. But when you scatter particles off an electron, the scattering pattern matches, with extraordinary precision, what you'd expect for a target with no size at all. A true mathematical point. No deviations, no hints of structure, no evidence of a finite radius. As far as the scattering data can tell, the electron is a dimensionless point. Let me be more specific about how this works because the details matter. When two charged particles interact, they exchange photons. This is the quantum mechanical description of the electromagnetic force. The electrons repel each other by exchanging virtual photons, particles that carry the force between them. The mathematical description of this interaction is provided by a theory called quantum electrodynamics, or QED. QED makes incredibly precise predictions about how electrons should scatter off each other and off other particles. If the electron were a tiny ball with a finite radius, those predictions would change. The scattering pattern at high energies and large deflection angles would differ from the point-like prediction. The larger the electron's radius, the bigger the deviation. So by performing scattering experiments at higher and higher energies, which corresponds to probing smaller and smaller distance scales, physicists can test whether the electron has any structure. The connection between energy and distance scale is crucial and worth understanding. In quantum mechanics, particles also behave like waves. Every particle has an associated wavelength called the de Broglie wavelength, named after the French physicist Louis de Broglie, who proposed the idea in 1924. The wavelength is inversely proportional to the particle's momentum. Higher momentum means shorter wavelength, and shorter wavelength means you can probe smaller structures. It's similar to how you need shorter wavelengths of light to see smaller details under a microscope. Visible light has wavelengths of a few hundred nanometers, so it can resolve features down to about that size. Anything smaller than the wavelength of visible light is invisible to an optical microscope, no matter how good the lenses are. To see smaller things, you need electron microscopes, which use electrons with wavelengths thousands of times shorter than visible light. To probe even smaller structures, you need even higher energies and even shorter wavelengths. To probe the interior of a proton, you need particles with wavelengths of about 1 femtometer. To look for structure inside an electron, you need to go much smaller than that. This is why particle accelerators keep getting bigger and more powerful. It's not just about smashing things harder for the fun of it. Higher energy means shorter wavelengths, which means finer resolution. Every time physicists build a more powerful accelerator, they can probe smaller distances, looking for structure that previous experiments couldn't detect. It's like getting a more powerful microscope. Each step up in energy reveals a new layer of detail. Over the decades, experiments have probed the electron at smaller and smaller scales. In the 1980s and 1990s, electron-positron colliders like the Large Electron Positron Collider at CERN in Geneva reached energies that allowed physicists to probe the electron down to about 10 to the negative 18 meters. That's 1,000th of a femtometer, 1,000th of the size of a proton, 1,000,000,000th of a meter. At that almost incomprehensibly tiny scale, the electrons still look like a perfect point. No structure, no size, no deviation from the predictions of QED for a point-like particle. To put 10 to the negative 18 meters in perspective, this is about 100 million times smaller than a typical atom. It's about 1,000 times smaller than a proton. If you scaled an atom up to the size of a football stadium, 10 to the negative 18 meters would correspond to something about 1,000th of a millimeter across. That's the scale at which physicists have examined the electron and found nothing. No surface, no internal parts, no spatial extent, just a point. Now, what does it mean to say the electron is consistent with being a point? This is an important distinction that I want to make sure is clear, because it's subtle. When physicists say the electron is point-like, they're making a specific experimental claim. They're saying that at every distance scale they've been able to probe, down to about 10 to the negative 18 meters, the electron's behavior is indistinguishable from that of a true mathematical point. They are not saying they've proven the electron is exactly a point with zero size. That's a much stronger claim, and it's not one the experiments can make. There's a difference between saying we've looked down to this scale and found no structure and saying we've proven there is no structure at any scale. Think of it this way. Imagine you're looking at a ball from far away, and it looks like a perfect dot. You bring it closer, and it still looks like a dot. You use a magnifying glass, and it still looks like a dot. You use a microscope, and it still looks like a dot. You use an electron microscope, and it still looks like a dot. At every level of magnification you've tried, the ball appears to have no size, but that doesn't prove it's truly a point. It just means that if it does have a size, that size is smaller than the resolution of your best microscope. The electron is in the same situation. We've probed it down to about 10 to the negative 18 meters and found no structure. If the electron does have a size, it must be smaller than that. But it could be smaller. It could be 10 to the negative 20 meters, or 10 to the negative 25, or 10 to the negative 30, or it could truly be zero. The experiments can't distinguish between these possibilities. They can only set an upper limit. This upper limit is what physicists call an experimental bound. The current bound on the electron's size is roughly 10 to the negative 18 meters. This means the electron's radius, if it has one, is smaller than about 10 to the negative 18 meters. Below that, we simply don't know. The electron might have structure at smaller scales that we can't yet probe, or it might truly be a point. Current experiments can't tell us which. This situation is fundamentally different from what happened with the proton. When physicists probed the proton at scales of about 1 femtometer, they found clear deviations from point-like behavior. The scattering pattern changed. The proton was revealing its internal structure. Its quarks and gluons were showing up in the data. The proton is definitively not a point. It has a measured, well-defined size. With the electron, nothing like this has happened. No matter how hard we've looked, no matter how finely we've probed, the electron keeps looking like a point. Every new generation of experiments, every new increase in accelerator energy has pushed the upper limit on the electron's size to smaller and smaller values. And every time, the answer has been the same. No structure, point, to the precision we can measure. Let me take a moment to describe what these experiments actually look like in practice. The experiments that probe the electron's size involve particle accelerators, massive machines that accelerate charged particles to speeds very close to the speed of light. The Large Electron-Positron Collider at CERN, which operated from 1989 to 2000, was a circular tunnel about 27 kilometers in circumference, buried beneath the border of Switzerland and France. Inside this tunnel, beams of electrons and positrons were accelerated in opposite directions and made to collide head-on. Enormous detectors surrounded the collision points, recording every particle produced. By studying the collision products, physicists could test the predictions of QED with incredible precision. Those predictions assumed the electron was a point. If the electron had structure, the collision products would differ from the point-like predictions. They didn't differ. Everything matched the point-like prediction perfectly. The LEP collider has since been replaced by the Large Hadron Collider, which uses the same tunnel but accelerates protons instead of electrons. Other experiments, using different techniques, have also probed the electron's properties with extraordinary precision. Measurements of the electron's magnetic moment, its behavior in electromagnetic traps, and its interactions with photons all provide indirect constraints on its size. And all of these measurements are consistent with the electron being a point, down to the limits of experimental precision. There's another way to think about why this result is so striking. Consider the hierarchy of matter as we know it. Ordinary matter is made of atoms. Atoms are made of a nucleus and electrons. The nucleus is made of protons and neutrons. Protons and neutrons are made of quarks and gluons. At each level of this hierarchy, things have sizes. An atom is about 10 to the negative 10 meters across. A nucleus is about 10 to the negative 15 meters across. A proton is about 10 to the negative 15 meters across. Quarks, as far as we can tell, are also point-like, with experimental bounds similar to the electrons. At each level, the sizes get smaller as you zoom in. But the sizes don't just get smaller smoothly, they jump. The atom is about 100,000 times bigger than its nucleus. The nucleus is roughly the same size as the protons and neutrons it contains, and then you get to quarks and electrons, and the sizes drop below anything we can measure. There's a discontinuity, a break in the pattern. You go from things with measurable sizes to things that, as far as experiment can determine, have no size at all. This break marks the boundary between composite objects and apparently fundamental objects. Composite objects have sizes because their parts are spread out in space. The atom has a size because its electron cloud extends to about 1 angstrom. The proton has a size because its quarks are distributed over about 1 femtometer. But electrons and quarks, which appear to have no internal parts, also appear to have no size. If you have no parts, there's nothing to be spread out. There's no internal arrangement to define a spatial extent. And so the concept of size, at least the concept of size as we understand it for everyday objects, simply doesn't apply in the same way. This is where the comparison between the electron and the proton becomes really illuminating. The proton has a radius of about 0.84 femtometers. We know this because when you fire electrons at protons, the scattering pattern clearly shows that the proton has spatial extent. The incoming electrons interact with different parts of the proton at different angles, and the resulting pattern encodes the proton's size and charge distribution. The proton is like a fuzzy ball, not a hard sphere, but a region of space where quarks and gluons are buzzing around, creating a measurable charge distribution that extends over about 1 femtometer. Inside the proton, things are complex. There are 3 valence quarks, 2 up quarks, and 1 down quark. But there's also a sea of virtual quark-antiquark pairs constantly appearing and disappearing, and gluons zipping between the quarks. The interior of the proton is a dynamic, chaotic place. This activity gives the proton its rich internal structure. And it's this structure that scattering experiments detect. The proton is composite. It's made of stuff distributed over some region of space, And that's why it has a size. The electron has none of this. No internal quarks, no gluons, no sea of virtual constituents that show up in scattering experiments, no measurable charge distribution that extends over any detectable region. When you scatter particles off an electron, the result is perfectly consistent with everything happening at a single point. There's no evidence that the electron is made of anything, no evidence that it has parts, no evidence that it has any spatial extent at all. This doesn't mean the electron is simple in the sense of being boring. As we'll explore later, the electron in quantum field theory is surrounded by a cloud of virtual particles that give it rich and measurable properties. But this cloud is different from internal structure. The electron itself, the fundamental excitation at the center, appears to be a point. Let me also mention something about the experimental methods themselves that makes this result even more compelling. The experiments that probe the electron's size don't rely on a single measurement or a single technique. They come from multiple independent lines of evidence. Electron-electron scattering experiments test the electron's electromagnetic properties at high energy. Electron-positron annihilation experiments test its behavior when it collides with its antimatter counterpart. Precision measurements of the electron's magnetic moment test its quantum properties to extraordinary accuracy. All of these different approaches using different experimental setups, different particle beams, different detectors, and different analysis methods all converge on the same conclusion. The electron is consistent with being a point particle down to about 10 to the negative 18 meters. When multiple independent experiments all agree, physicists take the results seriously. It's not one experiment that might have a flaw. It's a consistent picture from many experiments, all pointing the same way. So where does this leave us? We've probed the electron down to scales about 1,000 times smaller than the proton. We've used the most powerful accelerators ever built. We've analyzed data with sophisticated mathematical tools developed over a century of particle physics. And the answer, consistently and repeatedly, is that the electron has no detectable size. If it's a ball smaller than 10 to the negative 18 meters. That's so small that if the proton was scaled up to the size of a basketball, the electron's maximum possible radius would be smaller than a grain of fine dust within that basketball. And that's just the upper limit. The actual size could be much, much smaller. Or it could be exactly zero. This result is robust. It has been confirmed by decades of experiments across multiple generations of particle accelerators. It's one of the best established facts in particle physics. It is not controversial among physicists. There is no significant minority of researchers who believe they found evidence for the electron having a finite size. The consensus is firm and well supported by data. And yet the result remains deeply strange. Because the electron is not nothing. It has mass. It has charge. It has spin. It has a magnetic moment. It interacts with every atom in your body, in every piece of matter you've ever touched. It is one of the most consequential objects in the physical universe. Without electrons, there would be no chemistry, no molecules, no solid matter, no liquids, no life. Every chemical bond that holds your body together depends on electrons. Every photon of light you've ever seen was emitted or absorbed by an electron. The screen or speaker you're using to experience this right now works because of electrons flowing through circuits. The neurons firing in your brain as you process these words are powered by the movement of ions. which are atoms that have gained or lost electrons. Electrons are everywhere. They do everything. They are responsible for essentially all of the material complexity of the physical world. And yet, they have no measurable size. That's the paradox. That's the mystery we're grappling with. Something enormously important, physically real, experimentally well characterized to extraordinary precision, and yet, apparently, possessing no spatial extent whatsoever. It's as if the most important brick in the wall has no dimensions, yet somehow the wall still stands. The scattering experiments tell us what the electron is not. It is not a tiny ball. It is not a little sphere of charge. It is not a composite object with internal parts. It is not anything that has a classical size in the way we normally understand size. But the experiments alone can't tell us what the electron actually is. For that, we need theory. We need the framework that replaced classical physics at the subatomic scale. We need quantum field theory. And quantum field theory has an answer that is stranger, more elegant, and more precisely confirmed by experiment than anything the classical picture could ever offer. It tells us that the electron is not a tiny object at all. It's something else entirely. Something that our everyday intuitions have no category for. Something that redefines what it means to exist in the physical world. And as we'll see, the answer is far more beautiful and far more strange than anyone in Thomson's time could have imagined. So the experiments have drawn a clear line. On one side, everything we can't find. No ball, no surface, no structure. On the other side, a particle that is undeniably real and staggeringly well measured. The question now isn't what the electron looks like at small scales, it's what kind of thing it is in the first place. And here's where things get fascinating. Because while the electron may not have a classical size, it is far from simple. In modern physics, the electron is described by a framework called quantum field theory. And in that framework, the electron is something entirely different from anything our everyday intuitions prepare us for. It's not a particle in the way you imagine a particle. It's not a wave in the way you imagine a wave. It's something new. Something that required an entirely new language to describe. And that description turns out to be one of the most precisely confirmed theories in the history of science. To understand what the electron really is in modern physics, we need to talk about fields. Not fields like meadows or farmland. Fields in physics. A field is something that has a value at every point in space. Think about temperature. At every point in a room, there's a temperature. Near the heater, it's warmer. Near the window in winter, it's cooler. The temperature varies from place to place, but it exists everywhere in the room. There's no point in the room that doesn't have a temperature. The temperature fills the room completely. That's a field. A scalar field specifically, because at each point it has a single value, a number. Another example is wind. At every point in the atmosphere, there's a wind velocity with a speed and a direction. That's a vector field. Electric and magnetic fields work the same way. A positive charge creates an electric field extending outward in all directions, getting weaker with distance but never reaching zero. These are fields in the physics sense. They're not things located at one spot. They're conditions that pervade all of space. Now, in modern physics, the fundamental objects that make up reality are not particles. They're fields. Every type of particle corresponds to a field that fills all of space. There's an electron field that permeates the entire universe. There's a photon field, also known as the electromagnetic field. that also fills all of space. There's a quark field for each type of quark. There's a field for neutrinos. There's a field for every fundamental particle we've discovered. These fields exist everywhere, at every point in space, at all times. They're always there. Even in what we call empty space, the vacuum, these fields are present. They're at their lowest energy state in the vacuum, but they're still there. The vacuum isn't truly empty. It's filled with fields at their ground state, humming with what physicists call zero-point energy, the minimum energy that quantum mechanics allows a field to have. An electron, in this framework, is not a tiny ball sitting at some location in space. An electron is an excitation of the electron field. It's a ripple, a disturbance, a localized packet of energy in the electron field, like a wave on the surface of an ocean. The ocean is always there, stretching in every direction. Most of the time, it's relatively calm, but when something disturbs it, a wave forms. That wave is a localized disturbance. It has a position, sort of. It has energy, it moves, it interacts with other waves, but it's not a thing sitting on the ocean. It is the ocean, or rather it's something the ocean is doing. A particular configuration of the ocean's surface, a pattern of motion in the medium. The electron is like that. The electron field is always there, filling all of space. When the field is excited in a particular way, we observe what we call an electron. The electron is a quantum of the field, a discrete unit of excitation. It has definite properties because the field has specific rules about what kinds of excitations are allowed. Every excitation of the electron field has exactly the same mass, exactly the same charge, exactly the same spin, and exactly the same magnetic moment. That's why every electron in the universe is identical to every other electron. Not just similar, not approximately the same, identical. An electron in your fingertip right now is, in every measurable property, perfectly indistinguishable from an electron inside a star, burning 10 billion light years away at the edge of the observable universe. They're identical because they're all excitations of the same underlying field, and the field only allows one kind of excitation with those quantum numbers. Identity, in the deeper sense, comes from the field. This is a profound shift in how we think about reality. In the classical picture, the universe is made of stuff. Little hard objects with definite sizes and positions, bouncing around and interacting. In the quantum field theory picture, the universe is made of fields. Continuous, space-filling entities that can be excited in discrete ways. What we call particles are just the excitations. They're not fundamental objects in their own right. They're things that fields do. The fields are fundamental. The particles are derived. This has very concrete consequences. It explains why electrons can be created and destroyed. In the field picture, creating an electron is just exciting the electron field. It's like plucking a guitar string. The string was already there, quiet and still. You put energy in and it vibrates. The vibration is the particle. When an electron and a positron annihilate each other, the excitations of the electron field disappear, and excitations of the photon field appear in their place. Energy is transferred from one field to another. The fields just change their configurations. This framework also explains why the electron appears to be point-like in scattering experiments. In quantum field theory, the fundamental interaction between two electrons happens at a single point in space-time. Two excitations of the electron field interact by exchanging an excitation of the photon field, a virtual photon, and this exchange happens at a vertex, a point. The theory is built around these point-like interactions. There's no internal structure to smear the interaction over some region of space, because the electron isn't a little ball with an interior. It's an excitation of a field, and the excitation interacts at a point. Now, I need to tell you about one of the most remarkable aspects of the electron in quantum field theory. Because even though the electron is treated as point-like in its fundamental interactions, it is surrounded by a cloud of activity that gives it a rich and measurable physical presence. This is one of the most beautiful and strange features of quantum field theory, and understanding it is essential to grasping what the electron's true scale really means. In quantum field theory, the vacuum is not empty. It's a seething, frothing sea of virtual particles. These are particle-antiparticle pairs that spontaneously appear out of the quantum fields, exist for an incredibly brief moment, and then annihilate each other and vanish. They pop in and out of existence constantly, everywhere, all the time. This isn't speculation or metaphor. Virtual particles have measurable effects. Their existence has been confirmed by numerous experiments. Around every electron, this vacuum activity is modified. The electron's electric charge and its associated electric field influence the virtual particles in its vicinity. Specifically, virtual electron-positron pairs that pop into existence near the real electron become polarized. The virtual positrons, being positively charged, are attracted slightly toward the real electron. The virtual electrons, being negatively charged, are pushed slightly away. This creates a screen of virtual charge around the real electron, partially cancelling its charge at a distance. Think of it like looking at a bright light through a fog. The fog dims the light, making it appear less bright than it really is. The virtual cloud dims the electron's charge, making it appear weaker than it really is at large distances. This effect is called vacuum polarization, and it has a measurable consequence. The effective charge of the electron depends on how closely you probe it. If you measure the electron's charge from far away, you see a slightly reduced value because the cloud of virtual particles is screening some of the charge. If you probe closer, penetrating deeper into the virtual cloud, you see more of the bare charge. The closer you get, the stronger the charge appears. This is called the running of the coupling constant, and it's been measured experimentally. At the energies accessible to the Large Electron-Positron Collider, the electromagnetic coupling constant, which is related to the electron's effective charge, increases measurably compared to its value at low energies. The change is small but definite, and it matches the predictions of quantum electrodynamics precisely. This means that in a very real sense, the electron does have a kind of spatial structure. Not in the classical sense of being a little ball with parts, but in the quantum sense of being surrounded by a cloud of virtual activity that changes character depending on the distance scale at which you observe it. From far away, the electron looks like a particle with a certain charge. Up close, the charge is different. The electron's properties depend on the resolution of your measurement. There's a distance dependence, a scale dependence, to what the electron looks like. And this scale dependence is one of the most important concepts in modern physics. This is a kind of scale that has nothing to do with a surface or a boundary. It's not a size in the classical sense, but it means the electron is not the same object at every resolution. What you see depends on how closely you look, and that idea that the properties of a particle can change depending on the scale at which you observe it is one of the deepest lessons quantum field theory has to teach. Physicists sometimes talk about the bare electron versus the dressed electron. The bare electron is the idealized, theoretical point particle with no virtual cloud. It's what you'd see if you could somehow strip away all the quantum corrections and look at the electron in its most fundamental form. The dressed electron is the real, physical electron that we actually observe. It's the bare electron plus its cloud of virtual particles, the complete package that interacts with other particles and produces the measurements we record in our experiments. Every measurement we've ever made of the electron is a measurement of the dressed electron. The bare electron is a theoretical abstraction that we never observe directly. What we interact with, what we measure, what participates in chemistry and electricity and magnetism is always the dressed electron, the point-like core surrounded by its quantum cloud. Now let me tell you about the single most impressive prediction in the history of physics. Because it involves the electron, and it demonstrates just how well quantum field theory describes this particle. The electron has a property called spin. Spin is an intrinsic angular momentum that every electron possesses. It's a quantum mechanical property with no precise classical analog. The electron behaves as if it's spinning on its axis like a tiny top, but it's not literally spinning. It's not a sphere rotating in space, because as we've established, the electron isn't a sphere. Spin is a purely quantum property, something that fundamental particles just have, built into their mathematical description from the start. You can't speed up or slow down an electron spin. It's always the same value, always 1/2 in the natural units physicists use. The electron's spin gives it a magnetic moment. Because the electron has both electric charge and spin, it behaves like a tiny magnet. It has a north pole and a south pole. It aligns with or against external magnetic fields. It precesses, wobbles like a gyroscope when placed in a magnetic field. And this magnetic moment can be measured with truly extraordinary precision using devices called penning traps, which confine single electrons in electromagnetic fields and observe their behavior for weeks or even months at a time. In simple quantum mechanics, the most basic prediction for the electron's magnetic moment gives a value characterized by a number called the G factor. The simplest theory predicts that the G factor should be exactly 2. But in 1948, the physicist Julian Schwinger calculated the first quantum correction to this value using quantum electrodynamics. He showed that the quantum vacuum, the cloud of virtual particles surrounding every electron, slightly modifies the electron's interaction with a magnetic field. The virtual particles contribute a tiny additional current, if you will, that changes the effective magnetic moment. His calculation predicted that the G factor should be slightly larger than 2. Specifically, he predicted a correction of alpha divided by 2 pi, where alpha is the fine structure constant, a fundamental number in physics equal to approximately 1 divided by 137. This correction amounts to about 0.12%, tiny but measurable. This tiny correction, this deviation of the G factor from exactly 2, is called the anomalous magnetic moment of the electron. And it has been both calculated and measured to astonishing precision. On the theoretical side, physicists have calculated the anomalous magnetic moment, including contributions from thousands upon thousands of Feynman diagrams. Those mathematical pictures that represent different ways virtual particles can interact around the electron. The calculation includes effects from virtual photons, virtual electron-positron pairs, virtual muon-antimuon pairs, virtual quarks, and even contributions from the weak and strong nuclear forces. The current theoretical prediction, which took decades of work by teams of physicists and required some of the most complex calculations ever performed, agrees with the experimental measurement to better than 1 part in a trillion. Let me say that again because it deserves emphasis. The theoretical prediction and the experimental measurement of the electron's anomalous magnetic moment agree to better than 1 part in 1 trillion. That's like predicting the distance from New York to Los Angeles and being accurate to within a few nanometers, roughly the width of a single strand of DNA. Or like predicting the circumference of the Earth and being off by less than the width of a human hair. It's one of the most precise agreements between theory and experiment in the history of science, possibly the most precise. No other theory in any branch of science comes close to this level of quantitative confirmation. And here's what makes this relevant to our discussion. This calculation assumes the electron is a point-like excitation of a quantum field. It assumes the electron has no internal structure and no finite radius. The entire calculation is built on the framework of quantum field theory, where the electron is a point particle surrounded by a cloud of virtual activity. And this framework produces a prediction that matches reality to 12 decimal places. If the electron had internal structure, if it were a tiny ball with parts, the prediction would change. The anomalous magnetic moment would be different, and the extraordinary agreement between theory and experiment would be destroyed. This is perhaps the strongest evidence that the electron really is point-like. Not just that scattering experiments can't find any size, but that a theory built entirely on the assumption of a point-like electron produces predictions that match reality to a precision that would be impossible if the electron had any significant internal structure at the scales we've probed. The theory works. It works better than almost any other theory in physics. And it works because the electron really does behave at every scale we've tested, like a point-like excitation of a quantum field. But there's a subtlety here that I don't want to gloss over. Quantum field theory, as powerful as it is, has its own issues with the concept of a point particle. Remember the problem from classical physics? If the electron is a point, the electric field at its location is infinite, and so is the energy. This same problem shows up in quantum field theory, but in a different form. When you calculate the contributions of virtual particles to the electron's properties, some of those calculations produce infinite answers. The electron's self-energy, the energy of its interaction with its own quantum cloud, comes out infinite if you don't handle the math carefully. Physicists developed a technique called renormalization to deal with these infinities. The basic idea is that the infinite contributions can be absorbed into redefinitions of the electron's mass and charge. You start with the bare electron, which has infinite self-energy, and you define the physical mass and charge as the values that are actually measured, which include the effects of the virtual cloud. The infinities cancel when you express everything in terms of the measured quantities rather than the bare quantities. Think of it like measuring your height while standing on a mattress. The mattress compresses under your weight, and your raw measurement includes both your actual height and the mattress's response to you. You can't separate the two by looking at the raw number alone. But if you define height as the measured value, the one that actually matters when you walk through a doorframe, you get a finite, useful answer. Renormalization does something similar. It defines the electron's properties in terms of what we actually observe, rather than trying to isolate a bare value that can never be measured. It sounds like a mathematical trick, and for a long time, many physicists were uncomfortable with it. Richard Feynman, who helped develop quantum electrodynamics, and shared the Nobel Prize for it in 1965, alongside Schwinger and Shinichiro Tomonaga, once called renormalization a dippy process. He said it was sweeping the infinities under the rug, and expressed genuine dissatisfaction with the mathematical sleight of hand involved. Paul Dirac, another founding figure of quantum mechanics, was even more critical. He regarded the renormalization procedure as fundamentally unsound and believed a better theory would eventually replace it. But here's the thing. It works. Renormalization produces finite, well-defined predictions that agree with experiment to extraordinary precision. The anomalous magnetic moment calculation I just described relies on renormalization at every step. Without it, the calculation would produce infinities rather than the incredibly precise prediction that matches experiment. So whatever renormalization is doing, it's capturing something real about how physics works. The infinities aren't a sign that the theory is wrong. They're a sign that we're pushing the theory to the edge of its domain, and renormalization is the tool that lets us extract correct answers despite the mathematical difficulties. Some physicists view the infinities as a hint that quantum field theory isn't the final word. Maybe at some incredibly small distance scale, smaller than anything we can currently probe, the point-like picture breaks down. Maybe there's new physics at those scales that would make the infinities go away naturally. String theory, for instance, proposes that electrons and other fundamental particles aren't points at all. They're tiny vibrating loops or strands of energy with a characteristic length of about 10 to the negative 35 meters, the Planck length. Different vibration patterns of the string would correspond to different particles. An electron would be one vibration mode, a photon another, a quark yet another. At that scale, the point-like description would fail, and the infinities would be resolved because the string's finite extent would smear out the interactions over a tiny but non-zero distance. But the Planck length is 17 orders of magnitude smaller than the current experimental bound on the electron size. It's so far beyond our ability to probe that it might as well be in another universe. We have no experimental evidence for or against strings at that scale. What we do know is that between the scales we've probed, down to about 10 to the negative 18 meters, and whatever might happen at the Planck scale, around 10 to the negative 35 meters, there's an enormous range of distance scales about which we know essentially nothing regarding the electron structure. That's 17 orders of magnitude of unexplored territory. 17 factors of 10. To put that in perspective, the difference between the size of a single atom and the diameter of Earth is about 17 orders of magnitude. The gap between what we've measured and the Planck scale spans the same distance ratio as the gap between one atom and an entire planet. There could be a lot of physics hiding in that unexplored range. But within the range we have explored, the picture is clear. The electron behaves exactly as quantum field theory predicts for a point-like excitation. Its interactions are point-like. Its scattering behavior is point-like. Its magnetic moment matches the point-like prediction to 12 decimal places. The quantum cloud of virtual particles around it creates measurable, distance-dependent effects that are precisely described by the theory. The electron is not a simple object. It's a rich, dynamic entity. But its richness comes not from having internal parts arranged in space, like a proton's, quarks, and gluons, but from the quantum activity of the fields that surround it and interact with it. Let me try to paint a picture of what the electron looks like in quantum field theory. as best as words can capture something so alien to everyday experience. Imagine a vast, silent hum filling all of space, a background vibration present everywhere, at every point, at all times. Now imagine that at one location, the hum intensifies. A concentrated note rings out. A localized spike of energy rises from the background. That's the electron. It's not sitting in the field. It is the field, locally excited. Around this excitation, the field is never perfectly calm. Quantum mechanics forbids it. The uncertainty principle guarantees that there's always some activity, some fluctuation, some disturbance near the electron. Virtual particle-antiparticle pairs bubble up and disappear in the electron's vicinity. Virtual photons are constantly being emitted and reabsorbed. The electron is perpetually interacting with its own quantum field and with all the other quantum fields that fill space. This bubbling, fluctuating cloud of virtual activity is what gives the electron its measured properties, its mass, its charge, its magnetic moment. All of these are shaped by the virtual cloud. Strip away the cloud and you'd have the bare electron, a theoretical abstraction with different mass and charge that we never observe directly. The physical electron, the one that participates in atoms and chemistry and everything else, is always the dressed electron, always accompanied by its entourage of virtual activity. This picture resolves the classical paradox we started with. Remember the problem? If the electron is a point, the energy at its location is infinite, and its mass should be infinite. If it's a ball, it should fly apart from its own electric repulsion. Quantum field theory doesn't exactly resolve these issues in a clean philosophical sense. The infinities still appear in the math, but renormalization provides a consistent framework for extracting finite, correct predictions despite the infinities. And the theory doesn't require the electron to be a ball with internal stresses. The electron is a quantum excitation, not a classical object, and quantum excitations don't need to be held together by internal forces. The concept simply doesn't apply. Asking what holds the electron together is like asking what holds a wave together. A wave isn't a collection of parts bound by forces. It's a disturbance in a medium. The electron is a disturbance in a field. It doesn't need to be held together because it's not a composite object in the first place. This is the modern answer to what the electron is. It's a quantum of the electron field, a localized excitation with definite mass, charge, and spin, pointlike in its fundamental interactions, but surrounded by a measurable cloud of virtual quantum activity that gives it distance-dependent properties. Not a tiny ball, not a classical object of any kind, something genuinely new, a quantum entity that required a new framework of physics to describe, and that framework has proven to be the most precisely tested theory in the history of science. But accepting this answer raises a deeper question, one that goes to the heart of what we mean by scale when we talk about fundamental particles. If the electron has no classical size, if it's not a ball, if its physical properties come from quantum fields rather than from spatial extent, then what does it even mean to talk about the true scale of an electron? What are we really asking when we ask how big it is? And does the question even make sense for something fundamental? That's the question we need to confront next. And the answer may surprise you. So here we are. We've traced the electron from its discovery as a mysterious cathode ray particle in 1897 to its modern description as a point-like excitation of a quantum field. We've seen that classical physics tried to give the electron a size and failed. We've seen that experiments have probed the electron down to scales 1,000 times smaller than a proton, and found no structure whatsoever. We've seen that quantum field theory describes the electron not as a tiny ball, but as something entirely new, a quantum of a field, surrounded by a measurable cloud of virtual activity that gives it rich physical properties despite having no detectable spatial extent. And through all of this, one question has been lurking in the background, growing louder and more insistent with every answer we found. What does size even mean for something like the electron? Is the question itself broken? Are we asking the wrong thing when we ask how big an electron is? Let's think carefully about what size means. Not the physics definition, not the mathematical definition, the intuitive human definition, the one you carry around in your head without even thinking about it. When you say something has a size, what do you actually mean? You mean it takes up space? It occupies a region? If you tried to put something else in that same region, there would be a conflict. 2 basketballs can't occupy the same spot at the same time. 2 grains of sand can't overlap. 2 cars can't park in the same space. Size means exclusion. It means a thing claims a portion of space as its own and prevents other things from being there. This is so fundamental to our experience that it feels like a law of nature. And in a sense, it is. The reason solid objects feel solid, the reason your hand doesn't pass through a table, is ultimately because of the Pauli exclusion principle, a rule that says no 2 electrons can occupy the same quantum state in the same region. This principle is what gives matter its apparent solidity, its resistance to compression, its sense of occupying space, and ironically this principle involves electrons, the very particles that themselves may have no size, sizeless particles creating the illusion of solid, space-filling matter. The irony is remarkable. Size also means having an extent, a boundary, an inside and an outside. A basketball has an inside and an outside. The surface is where the inside ends and the outside begins. When you measure the size of a basketball, you're measuring the distance across this boundary. Every object you've ever encountered in daily life has this property. There's a region where the object is and a region where it isn't. Now here's the critical insight. For every object in your everyday experience, this boundary exists because the object is made of parts arranged in space. And the spatial extent of that arrangement is what we call size. This is true at every scale we've examined. Baseballs, molecules, atoms, nuclei, protons, all of them are composite. All of them have parts distributed across some region. And in every case, it's the distribution of those parts that gives the object its measurable size. Size is not a primitive property of matter. It's an emergent property. It emerges from the fact that things are made of other things, and those other things are spread out. Take away the parts, and there's nothing left to define a boundary, nothing to give the object extent. The concept of size has nothing to attach to. The electron, as far as every experiment has ever shown, has no parts. It's not made of smaller things. There's no internal arrangement, no constituents distributed over some region. Nothing inside that could define a boundary between inside and outside. And without parts, without internal structure, the classical concept of size simply has nothing to attach to. It's not that the electron's size is very small. It's that the concept of size, as we normally understand it, may not apply to the electron at all. This is a genuinely difficult idea to accept. Our brains evolved to understand a world of objects with sizes: rocks, trees, animals, tools. The idea that something can be physically real, can have mass and charge and measurable effects, and yet not have a size, goes against millions of years of cognitive evolution. It feels wrong, but the universe is under no obligation to match our expectations. It operates on its own rules, not ours. There's an important distinction that physicists make that helps clarify this situation. The distinction between composite particles and fundamental particles. Composite particles are made of smaller things. Protons are composite. They're made of quarks and gluons. Neutrons are composite. Atoms are composite. Molecules are composite. Everything you encounter in daily life is composite at some level. And all composite objects have size, because their parts are arranged in space and the arrangement has an extent. Fundamental particles, as far as we know, are not made of smaller things. Electrons are fundamental. Quarks are fundamental. Photons are fundamental. Neutrinos are fundamental. These particles sit at the bottom of the hierarchy of matter. There's nothing inside them. No substructure, no parts, no constituents that anyone has ever found. And this lack of parts is directly connected to their lack of measurable size. A fundamental particle doesn't have a size in the classical sense because there are no parts to be arranged. There's no internal structure to define a spatial extent. The particle just is. A quantum of a field, interacting at a point, with no interior to speak of. This might make you wonder whether fundamental particles really exist in space at all in the way we normally think about existence. And this is where the quantum nature of the electron becomes deeply relevant. In quantum mechanics, the electron doesn't have a definite position until you measure it. Before measurement, the electron is described by a wave function, a mathematical object that assigns a probability to finding the electron at each point in space. The wave function can be spread out over a large region or concentrated in a small region, but it's never a single point. It's always a distribution, a cloud of probability. When you hear that an electron in an atom occupies an orbital, this is what that means. The orbital isn't a path the electron follows. Like a planet orbiting the sun, it's a probability distribution. A three-dimensional cloud that tells you where the electron is likely to be found if you measure its position. In a hydrogen atom, the ground state orbital is a spherical cloud centered on the nucleus, most dense near the center and fading away with distance. The characteristic size of this cloud is about 1 angstrom, about 1/10,000,000th of a meter. This is often quoted as the size of the hydrogen atom. But here's the crucial distinction. The size of the orbital is not the size of the electron. The orbital is the region where the electron is likely to be found. It's the size of the electron's probability distribution, not the size of the electron itself. The electron, when you actually find it at a specific point in the orbital, is still point-like. It doesn't fill the orbital like a marble fills a bowl. It exists somewhere within the orbital as a point-like entity, and the orbital tells you the probability of finding it at each location. The orbital has a size. The electron, as far as we can measure, does not. Imagine a firefly in a dark cathedral. The cathedral is enormous. The firefly could be anywhere inside it. If you watch the firefly long enough, you could map out the whole space it tends to visit, and that space might be the full volume of the building. But the firefly itself is still tiny. The cathedral is where it lives. It is not how big the firefly is. The electron's orbital is the cathedral. The electron is the firefly. This distinction is important and often confused. People sometimes say the electron in a hydrogen atom is about 1 angstrom in size. What they really mean is that the electron's probability distribution in a hydrogen atom extends over about 1 angstrom. The electron's quantum behavior gives it a spatial presence in the atom, a region where it can be found, a region that determines the atom's size and chemical properties. But this spatial presence is not the same as having a physical size. It's more like the difference between asking where someone lives and asking how tall they are. The answer to where the electron lives is the orbital, about 1 angstrom across. The answer to how big the electron itself remains, as far as experiment can determine, consistent with 0. So when we ask about the true scale of an electron, we're actually confronting a question that doesn't have a simple answer. The electron has several different scale-related properties, and they're all different, and none of them correspond to a classical radius in the way that the radius of a baseball does. There's the classical electron radius, about 2.8 femtometers. This is a calculated number from classical electromagnetism, based on the assumption that the electron's mass comes from its electric field energy. It's a useful number that appears in certain physics formulas, but it doesn't represent the actual physical size of the electron. No experiment has ever found the electron to be this size. There's the Compton wavelength of the electron, about 2.4 times 10 to the negative 12 meters, or about 2.4 picometers. This is the wavelength of a photon whose energy equals the electron's rest mass energy. It sets the scale at which quantum effects become important for the electron. At distances much larger than the Compton wavelength, the electron behaves more or less like a classical particle. At distances comparable to the Compton wavelength, quantum effects like virtual pair creation become significant. The Compton wavelength is a quantum mechanical scale associated with the electron, but it's not the electron size in the way a diameter is, the size of a ball. It's a characteristic length that tells you something about the electron's quantum behavior. There's the de Broglie wavelength of the electron, which depends on its momentum. A fast electron has a short wavelength. A slow electron has a long wavelength. This wavelength determines the electron's wave-like behavior, its ability to diffract and interfere. It also determines how finely the electron can probe other structures. But again, this isn't the electron's size. It's a property of the electron's quantum state that changes depending on how fast the electron is moving. There's the size of the electron's orbital in an atom, typically about 1 angstrom. This determines the size of the atom and governs chemistry. But as we discussed, this is the size of the probability distribution, not the size of the electron. And there's the experimental upper bound on the electron's physical radius, about 10 to the negative 18 meters. This is the smallest scale at which we've probed the electron and found no structure. If the electron has a size, it's smaller than this, but it could also be exactly 0. Each of these numbers tells you something real about the electron. Each one is physically meaningful, but none of them is the electron's size in the simple, intuitive way that you can state the diameter of a tennis ball. The electron doesn't have that kind of size. It has a collection of characteristic scales, each relevant in different physical contexts, none of which corresponds to a hard surface or a definite boundary. The question, how big is the electron, doesn't have a single answer. It has several answers, depending on what you mean by size and what physical context you're asking about. This might feel unsatisfying. Humans like clean answers. We like to be able to say the electron is this big, point to a number, and feel like we understand. But nature doesn't owe us clean answers. And the fact that the electron scale can't be captured by a single number isn't a failure of understanding. It's a genuine feature of reality. The electron is a more subtle entity than a tiny ball, and describing it requires more subtle concepts than a simple radius. Now, could this picture change? Could future experiments reveal that the electron does have a finite size after all? This is absolutely possible. Physics is an experimental science, and every conclusion is provisional, subject to revision if new evidence appears. There are theoretical reasons to think the electron might have structure at scales far below what we've probed. Some theories beyond the standard model, the current best theory of particle physics, predict that electrons and other fundamental particles might have internal structure at very high energies. One class of theories, called prion models, proposes that quarks and electrons are themselves made of even more fundamental particles, called prions. In these models, the electron would be a composite object, like the proton, with internal parts distributed over some small region. The electron would have a finite size, probably extremely small, perhaps around 10 to the negative 20 meters or smaller, but definitively non-zero. If prions exist, the electron would finally have a size in the classical sense. It would have parts. It would have an inside. The concept of spatial extent would finally apply. Prion models have been around since the 1970s, proposed independently by several physicists, including Jogeshpati, Abdus Salam, and Haim Harari. But so far, no experiment has found any evidence for them. The electron continues to look fundamental and point-like at every scale we've tested. The absence of evidence for prions doesn't prove they don't exist, but it does mean that if they exist, they must be confined to scales smaller than anything we've yet probed. String theory, as I mentioned earlier, proposes that all fundamental particles, including the electron, are actually tiny, vibrating strings or loops with a characteristic length of about 10 to the negative 35 meters, the Planck length. If string theory is correct, the electron does have a size, but that size is so incredibly small that it's 17 orders of magnitude below the current experimental limit. We would need accelerators billions of times more powerful than anything that currently exists, or could realistically be built to probe the electron at this scale. For all practical purposes, the string length is experimentally inaccessible with any foreseeable technology. There's also the hierarchy problem, one of the great unsolved puzzles in particle physics. The electron's mass is incredibly small compared to the energy scales where gravity becomes important. The Planck energy, the energy scale at which quantum gravity effects become significant, is about 10 to the 22 times larger than the electron's mass energy. Why is there such an enormous gap? Why is the electron so light? Nobody knows. This gap is one of the most striking, unexplained features of the standard model. The electron's mass isn't predicted by the theory. It's measured and plugged in as a parameter. Nobody can explain from first principles why the electron has the mass it does rather than some other value. Some physicists think this hierarchy is a clue that there's new physics between the scales we've probed and the Planck scale. New particles, new forces, new structures that could reveal the electron to be composite after all. Others think the hierarchy might be explained by anthropic reasoning or by mathematical structures we haven't yet discovered. But this is speculation. We have no evidence for any of it yet. What we can say with confidence is this: at every scale we've probed, the electron is consistent with being a point-like fundamental particle. The theory that treats it this way, Quantum electrodynamics within the broader standard model produces predictions that agree with experiment to extraordinary precision. If the electron does have structure, that structure exists at scales far below what current experiments can reach. The electron might be fundamental all the way down, or it might have surprises waiting at smaller scales. We simply don't know. And perhaps the most profound thing about the electron scale is what it tells us about the nature of physical reality. We grow up in a world of objects, solid things with surfaces and sizes. We build our intuition around this world. We develop concepts like big and small, inside and outside, surface and volume. These concepts serve us beautifully in everyday life. They let us navigate the world, build tools, construct buildings, understand the objects around us. But when we push these concepts down to the most fundamental level of reality, they stop working. The electron doesn't have a surface. It doesn't have an inside and an outside. It doesn't have a volume. The concepts we use to describe everyday objects simply don't apply to it. This isn't because the electron is mysterious or unknowable. We know an enormous amount about the electron. We can predict its behavior with greater precision than almost anything else in science. It's not that we don't understand the electron. It's that understanding the electron requires us to abandon familiar concepts and replace them with new ones. Concepts like quantum fields, excitations, probability distributions, and renormalization. These new concepts don't map neatly onto our everyday experience. They can't be easily visualized. You can't build a mental image of a quantum field excitation the way you can build a mental image of a baseball. But they work. They describe reality with breathtaking accuracy. And they tell us something important about the universe. The universe at its most fundamental level is not made of tiny objects. It's made of fields and their excitations. The building blocks of reality are not smaller versions of the things we see around us. They're something else entirely. This is humbling. It means our everyday intuitions, the ones that feel so natural and so obviously correct, are just approximations. They work at the human scale. They work for baseballs and buildings and planets, but they break down at the scale of the electron. The universe is stranger and more wonderful than our intuitions suggest. And the electron, this ubiquitous, essential, extraordinarily well-characterized particle, is one of the clearest windows we have into that deeper strangeness. It sits right at the threshold between the familiar and the fundamental, between the world of objects and the world of fields, between what we can picture and what we can only describe mathematically. So what is the true scale of an electron? The honest answer is that the question contains an assumption that may not hold. The assumption is that everything real has a size. The electron challenges that assumption. It is real. It is measurable. It is everywhere. It holds atoms together, governs chemistry, enables electricity, makes life possible. But it may not have a size in any classical sense. Its true scale might be 0, or it might be so small that no experiment in the foreseeable future could detect it, or the concept of scale might simply not apply to it in the way it applies to a proton or a basketball. What we can say is this: the electron carries several length scales, each tied to a different aspect of its physical behavior. Its Compton wavelength sets the quantum scale. Its orbital sizes in atoms set the chemical scale. Its classical radius appears in certain electromagnetic formulas. Its experimental upper bound tells us how finely we've probed and found nothing. Each of these scales is real and meaningful, but none of them is the electron's size. In the simple sense, the electron is not a tiny version of a familiar object. It's something genuinely different from anything in everyday experience. It's a fundamental quantum of a field, point-like in its interactions, rich in its measurable properties, and resistant to being captured by any single number that we could call its size. There's something beautiful in this. The universe didn't have to be this way. It could have been turtles all the way down, smaller balls made of even smaller balls made of even smaller balls, each with a definite size, all the way to infinity. Instead, the universe seems to have a bottom, a level at which the concept of an object with a size gives way to something more fundamental. Fields and their excitations, entities that have properties and obey rules, but don't occupy space in the way that familiar objects do. The electron is our best example of this. It's the place where the familiar world of objects ends and the quantum world of fields begins. It's the boundary between the world we evolved to understand and the world as it actually is. Every atom in your body contains electrons, trillions upon trillions of them. They're in your skin, your bones, your blood, your brain. They're holding the molecules of your body together right now. The light entering your eyes as you experience these words was emitted by electrons somewhere and will be absorbed by electrons in your retina. The electrical signals in your neurons that are processing these words right now are carried by the movement of ions, which are atoms that have gained or lost electrons. You are, in a very direct sense, a structure built and maintained by electrons. And those electrons, every single one of them, as far as any experiment has ever been able to determine, have no measurable size. You are a being made of parts that have no parts. A structure built from building blocks that take up no space. A physical entity whose most fundamental components may have no physical extent at all. That's the paradox of the electron scale. And it's not a paradox that needs to be resolved. It's a paradox that needs to be appreciated. It tells us something fundamental about the nature of existence. Something that no amount of everyday experience could have prepared us for. Something that required centuries of careful experiment and theoretical innovation to uncover. The building blocks of reality are not what we expected. They're not tiny balls. They're not small versions of familiar things. They're quantum excitations of fields, point-like and powerful, holding together the entire material world without taking up any space at all. The next time you hold something solid in your hand, a stone, a coin, a cup of coffee, ask yourself what solidity actually is. Your fingers don't sink through the object because of electrons. The resistance you feel, the firmness of every surface you've ever touched, comes from electromagnetic forces generated by particles that have no measurable extent. Solidity is an illusion built by sizeless things. Every texture, every weight, every sensation of contact traces back to electrons, and they are, by any classical measure, infinitely small. That is the true scale of an electron. Not a number, not a measurement, but a lesson. A lesson about what reality is made of and how profoundly different it is from what our eyes and hands and everyday experience would lead us to believe. The electron is physically real, experimentally confirmed, precisely characterized, absolutely essential to everything you see, touch, and experience, and it has no detectable size. That's not a failure of measurement, that's not a gap in our knowledge. That might just be what fundamental means. Thank you for joining me tonight. If you found this journey worthwhile, a like or subscribe would mean a lot. It helps me keep making these explorations. And the next time you look up at the stars or down at your own hands, remember what you've learned. Everything you see, everything you touch, everything you are is held together by particles that may have no size at all. And somehow, from that paradox, all of this, the stars, the atoms, and you emerged. Good night, and may you never see the world quite the same way again.